there, bachas. How are you all? This is your ma'am Akshita, and I have come to help you understand the tricky chapter, which is coordination chemistry. Now, many of you guys are having this doubt. What exactly is coordination chemistry? What is it really? So, well, I'm here to help you understand coordination chemistry. And what all shall we be learning in our session today? In our session today, we shall be learning about some important terms. Some important terms to understand what coordination chemistry is. To understand coordination compounds, it is very important that there are certain terms you have clarity with. So that is what we shall be doing first, followed by Werner's theory, and we will then be looking at IUPAC nomenclature, that is naming of coordination compounds, IUPAC nomenclature, how to name coordination compounds, and finally we will be talking about the various kinds of isomerisms that are shown by these compounds. Now you will be wondering, ma'am, but we have also learnt about VBT, which is valence bond theory. We have also learnt about CFT. So what about that? Well, I have divided this particular chapter into two parts. The first part is where we try to understand the certain terms to be able to have a better understanding of coordination compounds. Then we will learn about something known as primary valency and secondary valency, which was given by Werner in his theory. After that, we will be learning how to name the compounds. And we shall be learning about isomerism, and all of these four belong to part 1. So as I told you, I have divided this chapter into two basic parts. The first part consists of these particular topics. The second part, however, will deal with your VBT and CFT, along with their features and drawbacks. So this is how we have divided this particular chapter. So now let's try to understand what exactly is a coordination compound. So beta, coordination compound are those compounds which are formed by the combination of two or more salts, okay, which retain their identity in solid as well as liquid state. Beta. All right, as well as liquid state. So for example, if you ask me, I can write coordination compound like this. Okay. Now, if I put this through a water solution, all right, it will dissociate to give rise to this. It will dissociate to give rise to this. However, whatever is there in the bracket, that is not undergoing any difference. So this particular entity which is within the brackets is nothing but your coordination compound. All right. Now, ma'am, why only within the brackets? Why not outside of the brackets? We will be able to understand that when we get a certain few terms. So let's start off with the terms. Now, coordination entity. What is this coordination entity, ma'am? What exactly is this coordination entity? So as you can read, a coordination entity is a central metal atom or ion with a fixed number of ions or molecules linked to it. So when you look at cobalt, Cl3, NH3, okay, this particular cobalt, it is linked with 3 chlorine molecules, 3 chloride molecules, and 3 ammonia molecules. Right? So this particular central metal atom along with chloride and ammonia within the enclosed bracket is known as the coordination entity. So when you look at this particular example, nickel with cobalt taken 4 times, nickel with cobalt taken 4 times. This is a coordination entity. This entire thing is a coordination entity. So the compounds, or I would rather say the central metal atom with the various other entities, okay, the central metal atom along with the various ions, okay, or molecules having a fixed number when enclosed in square bracket is said to be coordination entity. All right, and here are a certain few examples for that. Then what is the central atom, ma'am? So see, in a coordination entity, the central atom is always a metal. The central atom is always a metal, and around this particular metal, will you see that there are various ions or molecules that are present. So in a coordination entity, the central atom or ion is the atom or ion to which a fixed number of, what you need to keep in mind is fixed number of ions or groups are linked in a definite geometrical configuration. Now, to understand this geometrical configuration, we will talk about valence bond theory, and there you will understand the various geometrical configurations. But what you need to understand is that a central metal atom or a central atom is nothing but the atom around which fixed number of molecules or ions are present having a particular geometry. All right. So the central atoms or ions in the coordination entities for this particular one is nickel, Ni plus 2. Over here it's cobalt, Co plus 3. And over here it's iron, Fe plus 3. Now these central atoms or ions are known as Lewis acids. Ma'am, metals? Lewis acids? What are you saying? No, but these ions that are there, no, when you hear the term coordination compound. When I say ionic compound, what comes to your mind? Ionic bond. Covalent compound, covalent bond. Coordination compound, coordination bond. There is a coordinate covalent bond that is present. Now, what is this coordinate covalent bond, ma'am? Coordinate covalent bond is a special type of covalent bond. All right, where an element having excess electrons, that is lone pairs or ions, lone pairs or electrons, is donating it to a electron deficient species. So here these ions that you're looking at, these ions, fixed number of ions or groups, okay, these are known as ligands. So to this particular metal, a ligand is donating its electrons. Now, what do you know about Lewis acid? Lewis acids are electron acceptors. Our metal is accepting the electrons, right, from the ligand to fulfill its octet. Thereby, metal acts as a Lewis acid. And with respect to the ligand, the ligand is donating electrons, is it not? Thereby, it becomes a Lewis base. Ma'am, ligand? Yes, ligand. Ligands are nothing but these ions or molecules that are attached to the central atom, which is nothing but our metal. So the fixed number of ions or molecules that you're talking about, which are present around the central metal atom, are known as ligands. Now, these ligands can be ionic or they can be neutral, beta. They can be both ionic or neutral. Simple ions such as Cl minus is there. Small molecules like water and ammonia is there. Now, water and ammonia, they are neutral, right? Large molecules are also there like NH2, CH2, CH2, NH2, right? And even macromolecules such as proteins are also examples of ligands, right? When a single donor atom such as Cl minus, H2 or NH3 binds to the ligand, They are known as unidentate. That is, they are donating a single pair of electron. Right? When a ligand attaches to two donor atoms, okay, when a ligand attaches to two donor atoms like CH2, NH2, CH2, okay, or oxalate, that is, when a ligand is donating one pair of electrons, it is unidentate. When it is donating two pairs of electrons, it becomes bidentate, right? Bidentate. Or when it donates many more atoms, okay, many more atoms, okay, many more atoms, it becomes polydentate, right? So that's about ligands. Now, what is a coordination number? I told you multiple times that what did we understand? We were talking about coordination entity. That a central metal atom having fixed number of ions or molecules around itself in a particular geometrical fashion, right? But what did we focus on the term? Fixed. We focused on the term fixed. Now, coordination number talks about this. A metal ion's coordination number is the number of ligand donor atoms to which it is directly bonded. To which it is directly bonded. And let me tell you, this particular coordination number is fixed. If a metal will have, if it can have 5 ligands, it will have 5 ligands. If it can have 6, it will have 6. That's about it, right? So this particular coordination number that we're emphasizing on is fixed. That is what you're supposed to know, right? So in their complex ions, when you look at platinum and chloride complex, what do you see? It has six chloride atoms attached to it. Over here, nickel and ammonia complex, it has 4 ammonia atoms attached to this nickel. Thereby, the coordination number of platinum and nickel becomes 6 and 4 respectively. Becomes 6 and 4 respectively. Right? So is the example over here. So is the example over here. That both ferrous and cobalt have a coordination number of 6 in these complexes. Now, you'll be wondering, ma'am, why 6? Here, you see that only 3 are attached, but beta, this is oxalate. One oxalate gives rise to 2 donor atoms, 2 donor electrons, like 2 pairs of donor electrons. Here there are 3, so 6. Ethylene diamine, EN, it is capable of giving rise to 2 pair of donor electrons. Here there are 3, so 2 into 3, 6. Right? So this is about your coordination number. Now, ma'am, what is this coordination sphere? So when you were talking about the coordination entity, I said that whatever is there in the particular square bracket, that is this square bracket that we are talking about, or this coordination sphere that we are talking about, is nothing but the boundary. Anything and everything that is within that boundary, within that particular square bracket, becomes a coordination compound. As a part of a coordination compound, I would rather say. So this particular coordination sphere that we are focusing on, that we are talking upon, is nothing but the square brackets that you see, right? And this acts as a demarcation, a boundary. The coordination sphere is made up of the center atom or ion and the ligands attached to it, which are surrounded in square brackets. The ionizable groups are referred to as counter ions because they are written outside the bracket. Okay, so the ones that are ionizable, are known as counter ions. So everything that is present outside the bracket becomes counter ion. Inside the bracket becomes a part of the coordination compound. I hope that is clear. So the coordination sphere in the complex, when you look at this particular complex, K4, FeCN6, right here, this is the coordination number, 6 is the coordination number, Cn is the ligand, Fe is the metal atom, and the square that you see is the coordination sphere. And this K4 over here that you see is nothing but your counter ions, which is capable of undergoing ionization. Right? Which is capable of undergoing ionization. How, ma'am? When you look at this, K4, FeCN This ionizes in water to give rise to 4K plus ions plus FeCN6 4 minus 4 minus 4 minus 4 minus, right? So this automatically, this becomes a counter ion because it is ionizing. Everything that is present within the square bracket is not, is not eligible for ionization. It does not ionize, right? Now, what is a coordination polyhedron? A coordination polyhedron is defined as a pattern of arrangement of ligand atoms that are directly linked to the central atom. Now, see, beta, these ligand atoms that are there, they're not haphazardly, donating their electrons to the metal atom. There is a particular way and they're arranged in a particular fashion. All right? They have a particular geometry. This is what we will learn in VBT. That's not to worry about. But what you need to understand that they are not haphazardly present around the central metal atom, right? And this is nothing but the coordination polyhedron. They are present at, having a particular defined pattern. They can be octahedral, they can be square planar, they can be tetrahedral, right? So these are some of the examples about which you will learn in detail, don't worry. And let me be very, very honest with you. When you talk about coordination number, if the coordination number is 4, if the coordination number is 4, you get two types of geometries. One is tetrahedral and the other is the square planar. And when the coordination number is 6, when the coordination number is 6, there is just one geometry present, which is octahedral. 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 As you can see over here. Have a look. Right? Finally, oxidation number of central atom. Now see, beta, this central atom that is there, the central atom that is there, it happens to have an oxidation number. Okay, so the central atom in a complex is the charge it carries when the ligands and electron pairs that it shares are eliminated. Following the name of the coordinating entity, a Roman numeral in parenthesis represents the oxidation number. So basically, the oxidation number, which is nothing but the oxidation state, if you want to say, you can say it over here, of the central metal atom, which is with respect to the ionizable species, which is with respect to the counter ions. Okay, with respect to the counter ions and the ligands that are present. All right, so it is balanced. The counter ions charge and the ligands charge, it needs to be balanced for the species to be neutral. So to balance that, the charge which is present on the central metal atom is its coordination number, and it is always written in numeral, Roman numeral, in parenthesis when naming the compound. For example, we just learned K4 FeCN6. Now I want to know the oxidation number of ion. How will I know that? I know K4 dissociates as K4 plus FeCN6 taken to 4 minus. Now the oxidation number of ion is going to be, nothing but, let me take a different color. It's going to be nothing but, let's take it as X. Okay, let me take it as X plus Cn has how much? 6 into minus 1 is equal to, now the charge which is there is balanced by this, minus 4. So you get X minus 6 is equal to minus 4. X is equal to plus 2. So the oxidation number of ion over here is plus 2. As simple as that. This is how you calculate the oxidation number. Homoleptic and heteroleptic. See, beta, homo means same. Leptic, ligands. When all the ligands around the central metal atom are same, homoleptic. Hetero, different. That means the ligands, if they are different, even if one is different, then it becomes a heteroleptic complex. All right? All right? So with this, we will now start off Werner's theory. We will now start off Werner's theory. What you need to understand is all these terms that we have, understood, they will help you get a better understanding, of the compound, coordination compound, which will help you name it better, identify the isomerism better, right? Arrive at the geometry better, right? All right then. So beta, understand one thing, whenever there is a theory, it automatically becomes important, right? Any theory, automatically it becomes important from exam point of view. And it becomes important because it helps you understand the subject better. Okay, it has a very important role in understanding that particular subject better. So now when we talk about Werner's theory, as you know, Werner's theory was given by Alfred Werner. Now, before we arrive at what Werner said, we need to understand something that we have just learnt. We learnt that the number of ligands around the central metal atom, right, determines the coordination number, and a metal atom, okay, has definite coordination number in its definite coordination compound. That means the coordination number is fixed because the number of ligands around the central metal atom is fixed in a given compound. Whether you ionize it, do whatever with it, the coordination number does not change. It remains the same, right? For a given compound, for a given metal atom in a given compound. Okay. Okay, ma'am, this is clear. Then we learned something about counter ions, right? Now these counter ions can vary. They can vary. This is exactly what Werner is trying to demarcate with respect to, in context with, primary valency and secondary valency. The one which can be ionized and the one which cannot be ionized. The one which can be ionized is nothing but given by what? Your counter ions. And the one which cannot be ionized, stays intact, is nothing but the coordination number, which is nothing but your number of ligands. Now let's try to understand this better. Okay, this theory basically helps us understand the structure of coordination compounds. You can say that this was the beginning of trying to understand the structure of coordination compounds. You must be wondering, ma'am, why is it that we're learning about coordination compounds? Why are we doing so much with respect to it? The answer is very simple, beta. Coordination compounds play a huge role, or I would rather say a pivotal role, when it comes to bioinorganic chemistry. Organisms in nature, depend upon it as in it forms a major backbone, either in their metabolism, right, or in their food making process. That is why it is important. And as we already know, structure determines the function. So if you want to have a clarity about function, it is important you know the structure. So that is why understanding the structure came into picture, and Alfred Werner was one of the very, I would say, or I would rather put it this way, his theories were one of the most forthcoming theories, or the one which put light on primary valency and secondary valency. Now let's see what they are. Okay. He prepared and characterized a large number of coordination compounds and studied their physical and chemical behavior with simple experimental techniques. Okay. Werner proposed the concept of primary valency and secondary valency for a metal ion. Obviously, he gave the primary valency and the secondary valency for what, beta? For the metal ion. Now, binary compounds, when you look at binary compounds, CrCl2, CoCl2, PdCl2, they have primary valency 3, 2, 2 respectively. Okay. In a series of compounds of cobalt, this should be CrCl3, not 2. Yeah. In a series of compounds of cobalt, okay, cobalt 3 chloride with ammonia, it was found that some of the chloride ions could be precipitated as AgCl on adding excess silver nitrate solution in cold but remained in solution. Okay, so this is what you see, beta. This is what you see when you add silver nitrate. So over here, this COCl3.6 NH3 is nothing but CO NH3 taken 6 times Cl3. So all the 3 chloride ions are available for precipitation with silver nitrate. So you're getting 3 moles of AgCl. Now here COCl3.5 NH3, that is nothing but CO NH3 taken 5 times Cl Cl2. Now you see the coordination number is 6 in the first compound. It is 6 even in the second. And it remains 6 even in the third. But the counter ions, however, they vary because the counter ions are trying to fulfill the coordination number, right? So 6 groups in all, either chloride ions or ammonia molecules, or both remain bonded to the cobalt ion during the reaction. The compounds are formulated as shown above, where the atoms within the square brackets form a single entity which does not dissociate under the reaction conditions. Werner proposed the term secondary valency for the number of groups bound directly to the metal ion. In each of these examples, the secondary valencies are 6. Now, what is this particular secondary valency that he's talking about? Secondary valency is the non-ionizable valency. It is the non-ionizable valency, which is nothing but your coordination number. So, ma'am, what about primary valency? Primary valency naturally becomes the ionizable entity, which is nothing but your number of counter ions. This is the clear-cut demarcation that you need to understand. This is the clear-cut demarcation that you need to understand, beta. And you can look at it. You can look at the dissociation. 1:3. 1:2. This 1 is basically determining the coordination entity. 1:1, 1:1. Please have a look. And yes, they have different colors. Yellow, purple, green, and violet. Yellow, purple, green, and violet. Now, so basically, if we now have to summarize what Werner was trying to say, it simply is that in coordination compounds, there are 2 types of linkages. One is primary, one is known as primary valency, the other is known as secondary valency. This primary valency that we are talking about is ionizable. It is ionizable. And understand one thing. Anywhere where ionization comes into picture, it becomes non-directional. It is non-directional. Whereas secondary valency is non-ionizable. which is nothing but the coordination number of the metal atom in a given coordination compound. As simple as that. As simple as that, if I have to quote it. Right? And this particular secondary valency that is there is directional. It has a particular direction. That is what is summarized over here. That is what Werner tried to explain. That is what Werner tried to explain. Please have a look. Quickly have a look. Right? So this is our Werner's theory. This is our Werner's theory. And not just that, he further postulated that octahedral, tetrahedral and square planar geometrical shapes are more common in coordination compounds of transition metals. They are more common in the coordination compounds of transition metals. Right? So this all in all is explaining about, or Werner's theory basically explained about the coordination polyhedra in simpler terms. Right? He tried to explain the structure and he very nicely gave that these three, which is nothing but octahedral, tetrahedral and square planar geometrical structures, are the most common in transition metals. Right? Right? So this is about Werner's theory. Now, many a times you will be wondering that, ma'am, you said, you started in the beginning of the session saying that a combination of two or more salts, okay, in such a way that the entity that they are forming remains, okay, or does not lose its identity either in solid state or liquid state. Basically, it does not dissociate. So, ma'am, that is coordination compound. Okay, but what about double salts? So, what about double salts if you see? Double salts if you see, like more salts or carnallite. If you see, they dissociate. Yes, they are a combination of two or more salts, but they too dissociate. Whereas with respect to coordination compounds, the coordination entity remains intact. You can do nothing about it. With counter ions, yes, of course, counter ions will dissociate, but the coordination entity, that stays intact. All right. So this is about the difference between a double salt and a complex. Now, nomenclature. Now, when we are focusing so much on these compounds, it does not make sense to not name them. Right? We have to name them. Otherwise, how will we differentiate between any two particular coordination compounds? Right? So nomenclature, this nomenclature, that is naming procedure, was obviously given by IUPAC, International Union of Pure and Applied Chemistry. It was given by IUPAC, and this IUPAC, whenever IUPAC nomenclature comes into picture, please be prepared for a certain set of rules, because a certain set of rules will be introduced to you. And you're supposed to follow these rules in order to get the name right. All right? Now, one more thing is, if you know how to write the name, you will very easily be able to write the formula, write the molecular formula from the name given. So, either of the processes that you know, better it is. You know, it will help you understand the other. But let's focus on naming them, right? Let's focus on naming them, because naming is where many are, more often than not, we end up making mistakes. So if you name right, you will get the structure right. So let's learn the naming process. Okay. So additive nomenclature, principles of additive nomenclature is applied over here. Now, what are the rules? First things first, there is something that you have always learned, that is the positive entity comes first, the negative entity comes later. We always name the positive entity first, then the negative entity. For example, sodium chloride, calcium sulfate, calcium metal. So that is what is given, that the positive part of the complex compound will be named first, followed by the negative part. Always. The positive part will be named first, then the negative part will be named. As simple as that. Right? And even in naming, now once we have decided, let's say there is a coordination entity. Coordination entity is positive and the counter ions, let's say X is negative. So first you will name the coordination entity, then you will name the counter ion. But if at all the counter ion is positive and the coordination entity is negative, then in that particular case, you will again name the positive entity first, followed by the negative entity. Okay? This one thing you need to be clear. Positive first, negative later. Now, when we are naming the coordinate entity, be it positively charged coordinate or a negatively charged coordinate, when we are naming the coordinate entity, we will first name the ligands. That too in a particular alphabetical order. Alphabetical order you cannot play with, right? You have to name them in the alphabetical order, right? So ligands are named first, followed by, obviously, once you have named all the ligands in alphabetical order, you will name the central metal atom. You will name the central metal atom. So what have we learned so far? Positive entity first, negative entity second. Okay, when we are naming the coordination sphere, coordination entity, we will first, or coordinate entity, we will first name the ligands in alphabetical order, followed by the name of the central metal atom. Okay, now prefixes mono, di, tri. This is used to indicate the number of ligands. Mono, di, tri to indicate the number of ligands. But if complex ligands are used, then bis, tis, tetra, kis is used. Bis, tris, tetra, kis. Now here it is ethylene diamine, but we write it as En taken twice. So we will use bis ethylene diamine because it is a complex. It is a complex ligand. Right? Now, name of anionic ligands ends with O. For example, chloride Cl minus chlorido. Right? And cationic ligands will end with yum. It will end with yum. For example, and for neutral ligands, aqua is for water, AMMINE, double M, amine is for NH3, right? And nitrosyl is for NO, carbonyl is for Cu. These you need to remember. And what do I say? These are placed with parentheses. They are placed in parentheses. All right? Okay. Now, oxidation state of the central metal ion is indicated in Roman numerals. Now that we have learned how to name the ligands, once all the ligands are named, you will then name the central metal atom and then write its oxidation number. Very, very important. Very, very important. And when coordination entity was negatively charged, if the coordination entity is negatively charged, for example, if you take K4 Fe Cn taken 6 times. Now here the coordination entity is negatively charged. Fe taken 6 times 4 minus. It is negatively charged. You will end the name of the central metal atom with 8. ATE8. All right? ATE8. Now, here are some of the examples of anionic ligands, like HS minus is mercapto, Cn minus is cyano, NC minus is isocyano, fluoride is fluorido, hydroxo, azido, nitrido. Here are some of the examples, beta. Some of the examples. Okay. And here are some of the examples of how to name the compound. When you look at K4FeCN taken 6 times. This is nothing but first the positive part will be named K plus, right? So potassium. Then the ligand in the coordination sphere, hexacyanoferrate. Why? Because the coordination entity is negatively charged. Right? So here are some of your examples. Please have a look at it. Please quickly have a look at it. All right then. Here are some other examples to add on to it. Please have a look. So now that we have understood how to name the coordination compounds, let's talk about isomerism. Isomerism. What does isomer mean? Iso, same, mer, units. Basically, isomerism talks about having the same molecular formula but different arrangement of the atoms, right? Different arrangement of the atoms. So having same molecular formula but different arrangement of atoms, due to which they differ in one or more physical properties, right? I told you structure determines function. If structure changes, function changes. So they can have the same molecular formula, but if the structure is not the same, then what to do? Right? So that is what is there. So they differ in one or more physical properties and are called as isomers, and the phenomena is known as isomerism, and it is again of two types. One is structural isomerism and the second is stereoisomerism. Structural isomerism, stereoisomerism, the meaning is there in the term itself. Structural isomerism, that means they're having the same molecular formula but their structure is different, right? In stereoisomerism, they have the same molecular formula, yes, but the arrangement of the atoms in the space is different, right? The arrangement in the space is different. All right, so that is about isomerism. Let's have a look at some of the examples of structural isomerism. Now, structural isomerism again is of 5 types. Okay, starting off with ionization isomerism. Now, as you can read that isomers when ionized give different ions in solution or in molten state. They show ionization isomerism. Basically, look at the counter ion beta. Basically, the counter ion, when the counter ion exchanges itself, okay, with one of the ligands, but in the process, the coordination number is not changing. The secondary valency is intact, right? Such an ionization is known as, such an isomerism, sorry, is known as ionization isomerism, because upon ionizing this, you will get Br minus and here you will get SO4 2 minus, right? Next, linkage isomerism. Linkage isomerism. Now, this is seen in the case of ambidentate ligands, beta. Now, when you look at NO2. Now, in NO2, the nitrogen is capable of giving its lone pair, right? And oxygen is also capable of giving its lone pair, right? So such ligands are known as ambidentate ligands. And when the linkage, that is if the metal atom is linked with nitrogen, okay, but in the other case it is linked with oxygen, they become linkage isomers. For example, CONH3 taken 5 NO2 Cl2 is red when nitrite ligand is nitrito, and is yellow when nitrite ligand is nitrite. That is, in this particular compound, if the ligand is donating its electrons from oxygen, that is O, then it is red in color. Whereas if nitrogen is the one donating, it is yellow in color. It is yellow in color. Now, coordination isomerism, that is when exchange of ligands between two coordination spheres takes place in such a way that the coordination number of either is not hampered. It is known as coordination isomerism. Now look at this. Chromium is attached to 6 ammonia molecules, and here cobalt is attached to 6 cyanide molecules. Now the exchange takes place. Chromium gets cyanide and cobalt gets ammonia. Cobalt gets ammonia. All right. Now, talking about solvate isomerism, this is known as hydrate isomerism. Okay, in case of water as a solvent. Why? Because whenever there is water, okay, and it is dissolved in, free solvent that is having a lot of water molecule, what will happen is the water molecule will interact, okay? It will interact with the solvent molecules. In this case, isomers are different in number of water molecules as ligands and free solvent molecules in crystal lattice. Okay, in crystal lattice, they interact better. All right, however, when you let go of the solvent molecules, it will again get back to its normal structure. This is known as hydrate isomerism or solvate isomerism. Finally, coordination position isomerism. Now these are bridging ligands, okay? They're bridging the two metal atoms, OH and Cl. But look at this cobalt over here. It has 4 ammonia molecules and here it has 2 ammonia molecules and 2 chlorine. Now exchange takes place. Okay, 1 ammonia comes from this over here and 1 chlorine over here. As a result, the number of ligands on either sides becomes same. It becomes same. It becomes same. Basically, exchange is taking place within the molecule only, but around bridged ligands. This is known as coordination position isomerism. The position is changing, but the coordination sphere is not. It remains the same. So these are some of the examples of structural isomerism. Let's now look at stereoisomerism. Now, under stereoisomerism, beta, we have geometrical isomerism and stereoisomerism. Stereoisomerism. So, under stereoisomerism, we have geometrical isomerism and we have optical isomerism. Let's try to understand geometrical isomerism first. Geometrical isomerism, it is very commonly known as cis-trans isomerism also. But what you need to understand is geometrical isomerism in heteroleptic complexes. It has to be heteroleptic due to different possible geometrical arrangements of the ligands. The ligands occupy position either adjacent or opposite to one another. Okay. Now, geometrical isomerism is very much common in coordination number 4 and 6. Coordination number 4 and 6. This is very commonly known as cis-trans isomerism also. Now, look at it. When the two ligands, similar ligands, are on the same side, okay, Cl, on the same side, this is cis isomer. On the opposite side, trans isomer, right? So this is M. That M is the metal atom, A2B2 kind of a coordination compounds where A is the ligand, B is the ligand. Here we can say A has NH3, 2 NH3 molecules are there, and B has chlorine, 2 Cl molecules are there. At a square planar. Understand, tetrahedral molecules don't show geometrical isomerism because they're equidistant. Their arrangement is equidistant. Now, in square complex of MX2AB. Now, X2AB, same molecule on the same side, on the different side. On the different side. It is showing cis-trans isomerism. Now, for MABCD, ma'am, how does this show? We will keep one particular molecule intact, beta. One particular. And with respect to this, we will rotate the others. Okay? This PY will go here, NH2 will come here, NO2 will come here. Right? I'll give you an example. Let's say M, A, B, C, D. Now, I will keep A intact. I will move around M, A, D, B, C. A is intact over here again. I will again rotate it. M, A, C, D, B. Now I'll be like, ma'am, one more time we rotate it. But one more time if we rotate it, we'll again get back the same structure. That is what has been done here with respect to NH3. That is what has been done here with respect to NH3. As you can see. Alright, beta? Now, if there are bidentate ligands, okay. Now, when you look at CH2, NH2, which is glycine, and COO minus. So here both nitrogen and oxygen can donate electrons. But when it is attached, NH2 and NH2 is on the same side, it becomes cis. OO is on the same side, becomes cis. But when it is on the opposite sides, it becomes trans. It becomes trans. In octahedral complexes, beta, when it is there on any of the planes, this is cis. Opposite end, Cl, trans. Cl, trans. This is NH3 beta. Trans. Now, when you look at this one, when you look at this particular one, okay, En, cis, En on the opposite sides, trans. Or you can see with respect to chlorine also, chlorine, same plane, cis, chlorine, opposite plane, trans. Now, there's another one known as facial and meridional. When this one, okay, the axial one with equatorial ones. This is known as facial, one face. Whereas all the planar nitrogens come into picture. This is known as meridional. This is known as what, beta? This is known as meridional, and this is NO2. All the same molecules on the facial side, facial, meridional side, meridional. This is isomerism in coordination compounds, and we have spoken about geometric isomerism. Now, these are some of the points. That is, tetrahedral complexes, they do not show cis-trans isomerism. That is, they don't show geometrical isomerism. Okay, as all the four valencies are equal. Complexes having coordination number 1, 2, and 3 do not show geometrical isomerism. Coordination having complexes MA4, MA3B, MAB3 do not show cis-trans isomerism. The one having coordination number 6, MA6 and MA5B do not show coordination isomerism. And in octahedral, ABCDEF shows coordination isomerism having 15. Geometrical isomerism having 15 geometrical isomers, and only one such species is known, which is over here. Let's now talk about optical isomerism. Now, but optical isomerism, that is, they need to be, there's no idea of optical activity over here. What you need to understand is, they need to be mirror images. That is, both our hands are mirror images, right? They are mirror images. But if I impose the first one on the second one, is it getting imposed? It is not getting imposed. So, non-superimposable mirror images form optical isomers. That is what you need to keep in mind. Non-superimposable mirror images. They form optical, or they show optical isomerism. That is, they are capable of rotating the plane polarized light either in the clockwise direction or the anti-clockwise direction. If they are capable of rotating it in clockwise direction, then they are said to be dextrorotatory. If they are capable of rotating the light in anti-clockwise direction, they are known as levorotatory. Now look at it over here. These are optically active, both of them. But if you bring this particular molecule and place it on this, okay? But if you bring this molecule, the lever molecule, and place it on this, will it impose? It will not. It will not. Similarly, with the molecule over here, both of them thereby are optically active. That is, they are optical isomers. They are optical isomers. Please have a look. Please have a look. Please have a look. Please have a look. So this is about optical isomerism, bacha. And with this, we have come to the end of the first part, that is part 1 of coordination chemistry. Well, we shall now, not now, well, we will be learning about the part 2, which deals with valence bond theory and the crystal field theory in the second part. So please stay tuned for that, so that we will be able to cover that in detail with all the examples and exceptions that you come across, so that you have no doubts left. All right then, kids, until we meet next, keep smiling, keep revising, and stay healthy. Bye-bye.